Earth is covered in oceans. But across the entire solar system, worlds like this are almost impossible to find. So the real question is, why does Earth have water at all? For most of human history, we assumed oceans were a normal part of planets. But modern astronomy has revealed something shocking. Planets with abundant liquid water may be incredibly rare. So how did Earth become a water world while most planets stayed dry? To answer that question, we have to travel back to the violent birth of the solar system, when asteroids, comets, and planetary collisions shaped the fate of our oceans. Look at Mars, look at Venus, look at Mercury, at the Moon, at the thousands of rocky planets identified across the galaxy over the past 3 decades. Most of them are dry. Most of them are lifeless. Most of them have never held a single drop of liquid water on their surfaces. Not for a decade, not for a year, not for a moment in their multi-billion-year histories. And this is where the paradox begins. Because scientists know water itself is not rare. Water molecules, 2 hydrogen atoms bonded to 1 oxygen atom, form naturally inside interstellar gas clouds between stars. They coat the surfaces of dust grains in the cold regions of deep space. They exist in comets, asteroids, and frozen moons scattered across every solar system we have ever studied. Water, as a chemical compound, appears to be one of the universe's most common substances. But an ocean? A stable, warm, open body of liquid water sitting on the surface of a rocky planet, protected from evaporation and freezing, sustained across billions of years? That may be one of the rarest things in the observable universe. Start with Venus. Venus is nearly identical in size to Earth. It formed at roughly the same time from the same cloud of dust and gas in the same region of the early solar system. For a period spanning perhaps 2 billion years, Venus may have hosted liquid water on its surface. Computer models suggest a shallow ocean could have existed there, long enough, theoretically, for chemistry to become complicated, long enough for something interesting to have begun. Then something shifted. As the young sun gradually brightened, Venus, already wrapped in a thick carbon dioxide atmosphere, began absorbing more heat than it could release. Temperatures climbed. If oceans existed, they began to evaporate. The water vapor entered the atmosphere and trapped more heat still. A feedback loop formed, relentless and irreversible. The oceans, if they were ever there, boiled completely away. The hydrogen escaped into space. The oxygen bonded into crustal rock. The water wasn't merely gone, it was chemically erased. Today, the surface of Venus sits at 465 degrees Celsius. Its atmospheric pressure is 90 times that of Earth's surface. Sulfuric acid clouds wrap the entire planet in a permanent shroud. Venus didn't miss its chance to become an ocean world. It tried. The universe simply closed the window. Now look at Mars. Mars tells a different story, and in many ways a more haunting one. Because Mars did have water, not as a hypothesis, not as a model actually. The evidence is carved into the surface itself. Ancient river channels spread across the southern highlands. Valley networks branch like root systems through billion-year-old rock. The Valles Marineris, a canyon system stretching longer than the continental United States, shows signs of ancient water erosion along its walls and floor. Gale Crater, explored for years by NASA's Curiosity rover, was once a lake. The minerals confirm it. The chemistry confirms it. 3.5 billion years ago, Mars may have looked, from a distance, something like Earth. Then it lost its magnetic field. Without magnetism, the Martian atmosphere had no shield against the solar wind. The constant stream of charged particles flowing outward from the sun at millions of kilometers per hour. Over hundreds of millions of years, that wind slowly stripped the Martian atmosphere away, molecule by molecule. As atmospheric pressure fell, liquid water lost its ability to remain stable on the surface. Below a critical pressure threshold, water doesn't flow. It evaporates or freezes instantly. The rivers dried. The lakes vanished. The remaining ice buried itself at the poles and beneath the frozen regolith. Mars didn't die because it lacked water. It died because it couldn't hold the conditions that keep water liquid. And that's not the real problem. The real problem is how precisely and how improbably Earth's conditions have held together across 4 billion years. Earth has oceans because an extraordinary number of independent factors aligned simultaneously and sustained themselves across geological timescales. Remove any single factor, and the oceans disappear. The distance from the sun had to be right. Inside a narrow band astronomers call the Habitable Zone, where solar energy is sufficient for warmth, but not so intense that water boils away into space. Earth sits inside this band. Venus sits just inside its inner edge. Mars sits near its outer boundary. The margin, in astronomical terms, is almost nothing. The atmosphere required the right composition. Enough greenhouse warming to prevent global freezing, not so much that the planet became a furnace. Earth maintained this balance partly through geological feedback, volcanic outgassing releasing carbon dioxide, and the chemical weathering of rock slowly pulling it back out of the atmosphere. A planetary thermostat functioning across billions of years with no design and no guarantee of survival. Earth's size had to fall within a precise range, large enough to hold an atmosphere through gravitational force, small enough not to accumulate a crushing envelope of gas. The Moon, formed from a catastrophic early collision, stabilized the planet's axial tilt, preventing the wild seasonal oscillations that would have destabilized surface temperatures over geological time. And Earth retained its magnetic field, generated by the movement of liquid iron in the outer core, still active today, which deflects solar wind and protects the atmosphere. This is what Mars lost. This is why Mars has no ocean. Each of these factors operates independently. None of them guarantees the others. All of them had to survive simultaneously for billions of years without catastrophic disruption. That they did is not something we should take for granted. Step further out now. Leave the solar system entirely. The Kepler Space Telescope surveyed a region of the Milky Way containing roughly 150,000 stars. It confirmed more than 2,600 exoplanets. The majority are gas giants or hot Jupiters, massive worlds orbiting so close to their stars that surface temperatures reach thousands of degrees. Many are super-Earths, larger rocky worlds whose atmospheric pressures may be crushing and whose geologies may be far too violent for surface water to persist. Many orbit stars far more active than our Sun. Stars that regularly release flares powerful enough to strip planetary atmospheres in centuries rather than billions of years. Of those thousands of confirmed planets, only a fraction orbit within the habitable zone. Of those, only a fraction are small enough to be rocky worlds. Of those, we have not yet confirmed a single one with open liquid water on its surface. Not one confirmed ocean world beyond Earth. Not yet. Not anywhere. Consider what this means. The Milky Way alone is estimated to contain somewhere between 100 and 400 billion stars. If even 1% of those stars have rocky planets in their habitable zones, the number of candidates is still enormous. And yet the evidence gathered so far, from every telescope, every probe, every atmospheric measurement we have made, points in one direction. Ocean worlds are not the rule. They may be the rarest category of planet the universe produces. The search for liquid water on other worlds has consumed decades of scientific resources and billions of dollars in spacecraft. Mars orbiters, Europa missions. The James Webb Space Telescope, built to detect the chemical signatures of distant planetary atmospheres. What these instruments have returned is instructive. Water ice, yes, on moons, buried beneath surfaces, locked into polar caps. Water vapor occasionally in thin atmospheric traces. But liquid water, open and stable and sustained on a planetary surface. Absent. Every mission, every measurement, every telescope pointed at another world has returned the same answer. Not here. There is something psychologically embedded in how we experience Earth's water. We were born on this planet, so we assume it is representative. We assume that wherever conditions allow, water and life follow naturally. But the record of our own solar system tells a different story. 8 planets, 1 has oceans. 1 attempted it and lost everything to heat. 1 had water and surrendered it to a dying magnetic field. The others never came close. The odds, even here in our own small corner of the galaxy, are 1 in 8. Scale that across a universe of trillions of worlds, and the number approaches something closer to loneliness than abundance. We walk beside the ocean. We photograph sunsets over the water. We accept its presence as simply what a planet looks like, as if this is the natural condition of a world, as if water on a surface is ordinary. We have built entire civilizations on the assumption that Earth is the template. It is not the template. It is the exception. Most planets are airless, most are irradiated, most are frozen or scalded. Most have never known a wave, a tide, a current, a storm moving across open water. Most will never know what it is to have liquid on their surfaces at all. The universe is not wet. The universe is dry and violent and indifferent to the conditions life requires. What Earth has, these oceans, this atmosphere, this magnetic shield, this distance from the sun, this geological balance sustained across 4 billion years, is not a gift. It is not a design. It is a compounding of improbabilities so long and so specific that even in a universe of this scale, it may have happened only a handful of times. We are not the default. We are the anomaly. Earth is an ocean planet in a universe of deserts. The universe is full of water. Not as a poetic claim, as a measurable, documented scientific fact. Water molecules have been detected inside the gas clouds where stars are born. Vast interstellar nebulae hundreds of light years across, cold and dark, containing more water than every ocean on Earth, multiplied by numbers too large to visualize. They have been found coating the surfaces of dust grains drifting between star systems. Found frozen into the cores of comets that formed in the outer edges of our solar system 4.5 billion years ago. Found embedded in asteroids, in the atmospheres of giant planets, in the polar deposits of airless moons. Found most recently in the atmospheric signatures of planets orbiting other stars. Detected from billions of kilometers away by telescopes sensitive enough to read the chemical fingerprint of a world from across the galaxy. If water were enough, oceans would be everywhere. They are not. This is the central contradiction that sits beneath all planetary science. beneath the search for life beyond Earth, beneath every mission we have ever sent toward another world. Water, the molecule, is one of the universe's most common chemical compounds. Oceans, stable bodies of liquid water sustained on planetary surfaces, may be among the rarest structures in the observable universe. The gap between those two facts contains almost everything important about why Earth exists the way it does. Begin in the dark between stars. Interstellar space is not empty. It is filled with enormous clouds of gas and dust. Molecular clouds, astronomers call them. And inside those clouds, temperatures fall to within a few degrees of absolute zero. At those temperatures, atoms bond into simple molecules. Hydrogen pairs with oxygen. Water forms. Not as liquid, not even as ice in the familiar sense, but as thin molecular coatings on the surfaces of microscopic dust grains suspended across volumes of space larger than entire solar systems. These clouds are detected not by optical telescopes, but by radio telescopes sensitive to the specific frequencies at which water molecules absorb and emit radiation. Astronomers have identified regions of space containing more water than the human mind can meaningfully process. The star-forming cloud Bu Hydrae, located roughly 350 light-years from Earth, holds an estimated 10,000 times more water than exists in all of Earth's oceans combined. And W Hydrae is not exceptional. Molecular clouds like it are scattered across the galaxy by the thousands, each one a cold, dark reservoir of chemical potential, each one containing more water than any planetary surface could ever hold. None of it is liquid. None of it is an ocean. At those temperatures and pressures, water exists only as a trace coating on dust. Inert, frozen, dispersed across incomprehensible distances. It is water in the way that scattered iron atoms in a rock are iron. The presence of the element tells you nothing about the object's surface conditions. Now move inward. Come closer to a star. As a molecular cloud collapses under its own gravity and begins forming a solar system, temperature and pressure change dramatically depending on distance from the forming star. In the inner regions, where rocky planets eventually form, temperatures are high enough that ice vaporizes. Water doesn't accumulate there. It gets pushed outward by solar radiation and solar wind, away from the warming center, toward a boundary astronomers call the frost line. Beyond that line, roughly where the asteroid belt sits in our own solar system, temperatures fall enough for water ice to remain stable. This is why the outer solar system is dominated by ice. It is not coincidence. It is thermodynamics. Comets form beyond the frost line. They are ancient objects, some of the oldest material in the solar system, composed largely of ice mixed with rock and organic compounds. When their long, elliptical orbits bring them close to the sun, that ice vaporizes into glowing tails of gas and dust, visible from Earth across millions of kilometers. For decades, scientists believed comets might have delivered significant amounts of water to the early Earth, that our oceans might have arrived not from within the planet itself, but from space, carried in by billions of cometary impacts during a period known as the Late Heavy Bombardment. The answer, it turns out, is more complicated. The water in most Jupiter family comets carries a different hydrogen isotope ratio than Earth's ocean water. The match isn't exact. Comets may have contributed, but they were probably not the primary source. The water in Earth's oceans likely came from a different direction, from water-rich asteroids in the inner solar system, and from water locked inside the rocky material from which the planet itself formed. It did not arrive from outside. In large part, it was already here. But that's not the real problem. The real problem is not where the water came from. The real problem is what happens to water after it arrives. Look at Europa. Europa is the fourth largest moon of Jupiter, slightly smaller than Earth's moon, covered in a smooth shell of water ice marked by a complex network of cracks and ridges. Beneath that ice, heated by the gravitational flexing of Jupiter's immense tidal forces, there is an ocean, not a lake, not a small subsurface reservoir. An ocean estimated to contain more liquid water than all of Earth's oceans combined. Liquid for billions of years, warm enough near hydrothermal vents at the ocean floor to potentially support chemical reactions similar to those associated with life on Earth. Europa has more liquid water than Earth. It has had it for a very long time. It has no surface ocean. Its water is buried beneath an ice shell that may be anywhere from 15 to 30 kilometers thick, completely sealed from the surface, never exposed to space, never forming waves or tides visible from above. From the outside, Europa looks like a cracked, frozen billiard ball. The ocean it contains is entirely invisible. Now look at Enceladus, a small moon of Saturn, barely 500 kilometers in diameter. Enceladus is so reflective, it was initially overlooked as scientifically uninteresting. Then the Cassini spacecraft flew through plumes of water vapor erupting from cracks near its south pole. Geysers blasting liquid water directly into space, evidence of a warm subsurface ocean beneath the ice. Scientists detected silica nanoparticles in those plumes consistent with hydrothermal activity at the ocean floor. Hydrogen gas, a potential energy source for microbial life. Organic compounds. Enceladus has a liquid ocean. It has chemistry. It erupts that water into space with enough force that it becomes visible. It has no surface ocean. Then there is Titan. Saturn's largest moon is the only body in the solar system besides Earth. With stable liquid on its surface, rivers, lakes, seas, filled with an active hydrological cycle, moving liquid from surface to atmosphere and back. It rains on Titan. Rivers carve channels into the landscape. Seas large enough to hold surface waves sit near the poles. But Titan's seas are not water. They are liquid methane and ethane, existing at temperatures of minus 179 degrees Celsius. Water on Titan is rock. The ice that forms Titan's surface behaves with the rigidity of granite at those temperatures. In Titan's environment, water cannot be liquid. It can only be a structural material. Titan has seas, it has a hydrological cycle, it has no ocean of water. Every surprising place science has found water in the solar system reinforces the same conclusion. Water appears constantly, as ice, as vapor, as subsurface liquid sealed beneath kilometers of frozen shell, as trace atmospheric moisture, as ancient mineral deposits in rock that was once saturated, but is now completely dry. The solar system is rich in water. What the solar system almost entirely lacks is water in the specific phase and location that defines Earth. Liquid, open, on the surface, stable over geological time. The physics behind this is not mysterious. It is simply unforgiving. Water exists as liquid only within a narrow band of temperature and pressure. Below 0 degrees Celsius at sea level pressure, it freezes. Above 100 degrees Celsius, it boils. But those numbers are not fixed. They shift with atmospheric pressure. At lower pressures, water boils at lower temperatures. On the surface of Mars today, the atmospheric pressure is less than 1% of Earth's. If liquid water appeared on the Martian surface, even at temperatures above zero, it would instantly boil away. Not slowly, instantly. The pressure is too low to hold it in liquid form. On the other side of the balance, if a planet's atmosphere is too thick and its greenhouse warming too intense, temperatures rise above the boiling point regardless of pressure. Venus sits in this condition. Its surface is hot enough to melt lead. Even under the crushing pressure of its atmosphere, water cannot exist as liquid there. Between those extremes of too cold and frozen, too hot and vaporized, too pressurized and crushed, too thin atmosphered for liquid stability, lies a zone of conditions so narrow that the probability of a rocky planet landing inside it by chance and remaining there for billions of years should seem almost impossibly small. And yet Earth did. Earth maintained temperatures within this range, never globally freezing over permanently, never boiling into a Venus-style furnace, for 4 billion years. It did so without any fixed external stabilization. The sun's luminosity has increased by approximately 30% over the history of the solar system. The early Earth, receiving less solar energy, should have been frozen. It wasn't, and the geological record confirms liquid water on the surface as far back as 4.4 billion years ago. The planet somehow compensated for a dimmer sun through atmospheric chemistry, and then compensated again as the sun brightened, holding conditions within the liquid window across timescales that dwarf the entirety of multicellular life. This is not a story of abundance. This is a story of extraordinary constraint. Water fills the galaxy. It coats interstellar dust. It hides beneath the ice of distant moons. It erupts from geysers in the outer solar system. It drifts through the atmospheres of exoplanets as vapor, detected by spectrographs from light years away. But holding that water liquid on a surface exposed to the open sky across billions of years, under the pressure of one active star's constantly evolving output, within the gravitational influences of neighboring planets with the right atmospheric chemistry, performing a balancing act across geological epochs. That is something the universe almost never allows. A molecule is not an ocean, a comet is not a sea, buried ice is not a tide. The universe offers water in almost every form it can take. What it almost never offers is the conditions required to turn that water into something you could stand beside, something you could sail across, something that could support 4 billion years of unbroken chemical evolution. Everywhere we look, we find water. Everywhere we look, we find the wrong kind. Water is common. Oceans are not. There is a region around every star where, in theory, liquid water can exist on a planetary surface. Not too close. Where heat would strip oceans into vapor and drive runaway warming until nothing remained. Not too far. Where solar energy would thin and temperatures would fall until every molecule of surface water locked permanently into ice. Between those extremes lies what astronomers call the Habitable Zone, the Goldilocks Zone. The narrow band of orbital distance where conditions are, in principle, just right. It sounds reassuring. It is not. The habitable zone is one of the most important concepts in planetary science, and also one of the most misunderstood. Its name implies that planets within it are habitable. It implies that distance from a star is the governing variable. That if a planet orbits in the right place, water follows. that oceans are a natural consequence of correct positioning, that the zone itself provides some kind of protection. None of this is true, then. The habitable zone is not a guarantee. It is not even a strong indicator. It is a rough geometric boundary calculated from stellar luminosity and orbital distance, useful as a starting filter for planetary candidates, but meaningless as a prediction of surface conditions. A planet can sit perfectly inside the habitable zone and be completely, permanently, irreversibly dry. We do not need to search other star systems for examples. Our own solar system provides two. Venus is inside the habitable zone, not marginally, not barely clinging to its inner edge. Venus orbits at a distance where, under different atmospheric conditions, liquid water could theoretically be stable. The zone's inner boundary, as defined by most contemporary models, sits at roughly 0.95 astronomical units from the Sun. Venus orbits at 0.72, closer than the boundary, yes, but within the range that some models define as potentially habitable under high albedo conditions. More significantly, current models of Venus's ancient past suggest that billions of years ago, when the Sun was dimmer and Venus may have rotated more slowly, surface temperatures could have remained low enough for liquid water to persist for extended periods. The solar system's most hellish planet may once have been an ocean world, and it lost everything. The mechanism of Venus's destruction is called a runaway greenhouse effect, and understanding it reveals something critical about why the habitable zone is not enough. When sufficient water vapor enters a planetary atmosphere, either from volcanic outgassing or ocean evaporation, it acts as a greenhouse gas, trapping infrared radiation from the surface and raising temperatures. As temperatures rise, more water evaporates, adding more vapor to the atmosphere, trapping more heat. The cycle is self-reinforcing. Once it crosses a critical threshold, it cannot reverse itself through any natural planetary process. The oceans don't just dry up, they don't slowly recede. They boil entirely into the atmosphere, and then, exposed to ultraviolet radiation from the sun, the water molecules break apart. Hydrogen, the lightest element, escapes into space. Oxygen reacts with surface rock. The water is not merely gone, it is chemically destroyed and permanently lost. Venus sits in the habitable zone, and its surface temperature is 465 degrees Celsius. Now, look to the other side. Mars orbits at 1.52 astronomical units, just beyond most definitions of the habitable zone's outer edge, though some broader models include it within a colder, marginally habitable range. Early Mars, as established in Section 1, almost certainly had liquid water. The valley networks, ancient lake beds, and mineral deposits all confirm surface water activity that persisted for hundreds of millions of years during the Noachian period, roughly 4 billion years ago. Mars was not just passing through liquid water conditions. It maintained them long enough for complex sedimentary geology to develop, for lake floors to accumulate layered mineral deposits, for river systems to carve recognizable drainage patterns into the highlands. Then the water left, and the reason it left reveals the second way a planet can fail, even when correctly positioned. Mars lost its magnetic field approximately 4 billion years ago. The precise mechanism still debated, but likely related to the cooling and solidification of its smaller iron core. Without the magnetic dynamo that generates a protective magnetosphere, the Martian atmosphere had no defense against the solar wind. Charged particles streaming outward from the sun at up to 800 kilometers per second began interacting directly with the upper atmosphere. Ion by ion, molecule by molecule, the atmosphere was sputtered away. As atmospheric density declined, so did surface pressure, and as surface pressure fell below a critical threshold, approximately 0.6% of Earth's atmospheric pressure, liquid water could no longer remain stable on the surface. Water that tried to flow would immediately freeze or vaporize. There was no middle state. Mars didn't drift out of the habitable zone. It stayed in approximately the same orbit, but it lost the internal machinery required to maintain conditions within that zone. The zone around it changed nothing. The conditions on it changed everything. It gets worse. Because even these two examples, Venus and Mars, both dramatic in their failures, do not capture the full scope of how inadequate the habitable zone concept is as a filter for ocean worlds. Beyond our solar system, the problem compounds in ways that took planetary scientists years to fully recognize. Consider tidal locking. Many planets within the habitable zones of smaller, cooler stars, red dwarfs, which are by far the most common type of star in the galaxy, orbit so close to their host stars that gravitational forces lock their rotation to their orbital period. One side of the planet faces the star permanently. The other faces permanent darkness. The day side can reach temperatures hot enough to vaporize surface water. The night side can fall cold enough to freeze atmospheric gases solid. Whether a stable middle ground temperature zone persists on the terminator, the boundary between permanent day and permanent night, depends on complex atmospheric dynamics that vary from planet to planet. Many habitable zone planets around red dwarfs may be tidally locked into conditions that preclude stable liquid water on any significant fraction of their surfaces. Consider stellar activity. Red dwarf stars are not just small and cool. They are magnetically violent, particularly in their youth. They regularly release flares, bursts of ultraviolet radiation, and charged particles far more intense than anything the sun produces, that can strip planetary atmospheres far more rapidly than the slow sputtering that drained Mars. A planet orbiting in the habitable zone of a young, active red dwarf might lose its entire atmosphere within the first billion years, before life has had any meaningful opportunity to develop. The zone defines the right distance. The star's behavior makes that distance irrelevant. Consider atmospheric composition. The width of the habitable zone, how broad or narrow that band of viable orbital distances is, depends entirely on the composition and density of a planet's atmosphere. A planet with a thick carbon dioxide atmosphere can remain warm enough for liquid water at orbital distances where an atmosphere-free world would be completely frozen. Conversely, a planet with a reflective atmosphere can remain cool enough to hold liquid water at distances where a dark, absorbing surface would overheat. The zone is not fixed. It shifts with every atmospheric variable, and those variables, the exact mixture of greenhouse gases, the planet's albedo, the efficiency of its carbon cycle, are determined by geological and geochemical processes that have nothing to do with orbital distance. This is the failure of the simple model. Habitability is not a location, it is a state. A complex, dynamic, multivariable state that requires not just the right distance from a star, but the right atmospheric composition, the right internal geology, the right magnetic shielding, the right planetary mass, the right orbital stability, and the right history of impacts, volcanic activity, and climate feedbacks, all operating simultaneously and coherently across billions of years. Distance is one input into a system with dozens of critical variables. Weight it accordingly. And this changes everything about how we should think about Earth. Earth does not have stable liquid water because it orbits in the habitable zone. It orbits in the habitable zone and it has a carbon-silicate cycle, a long-term feedback mechanism by which volcanic outgassing releases carbon dioxide into the atmosphere, and the weathering of silicate rock pulls it back out, regulating atmospheric greenhouse concentration over millions of years. When the planet cools, weathering slows, carbon dioxide accumulates, and warming increases. When the planet warms, weathering accelerates, carbon dioxide is drawn down, and cooling follows. This cycle is not perfect, it is not fast, but it operates across geological timescales in a direction that resists extreme deviation. Without this cycle, Earth's position in the habitable zone would be insufficient. The sun has brightened by 30% since the solar system formed. Early Earth, receiving less energy, should have been frozen under a dim young sun. The geological record says it wasn't. That liquid water existed on the surface as early as 4.4 billion years ago, during a period when solar output was far lower than today. The carbon-silicate cycle, along with higher concentrations of greenhouse gases in the early atmosphere, compensated. Later, as the sun brightened, the cycle drew down excess greenhouse gases, preventing runaway warming. The thermostat adjusted. The oceans remained. This is not the behavior of a planet simply sitting inside a convenient geometric zone. This is the behavior of a planet with functioning climate regulation. A geochemical system capable of compensating for external changes across billion-year timescales. Position enables it. Geology sustains it. The habitable zone provides the window. Earth's internal processes have kept the window open for 4 billion years. Most planets do not have this. We do not know what fraction of rocky habitable zone planets develop the specific geological conditions, the right mix of volcanism, tectonics, and surface chemistry, to sustain long-term climate regulation. We have exactly one confirmed example. Every extrapolation from that example is at best an informed estimate. What the scientific record makes clear is that habitable zone membership is necessary, but nowhere near sufficient for an ocean world. Venus is inside the zone, scorched and airless. Mars is near the zone, frozen and barren. Of the thousands of exoplanets confirmed in recent years, only a small number occupy habitable zones around their host stars. And of those, nearly none have confirmed surface water. Every habitable zone candidate discovered generates excitement, precisely because the bar is so low. We get excited about position because we have almost nothing else to observe from this distance. But position is not the answer. Position is just the beginning of a much harder question. A planet can orbit in the perfect location and still freeze. It can orbit in the perfect location and still boil. It can lose its atmosphere, lose its magnetic shield, lose its geological regulation, lock its rotation, suffer catastrophic impacts, accumulate the wrong gases, reflect too much light, absorb too much radiation, oscillate between ice ages severe enough to freeze all surface water. All while sitting precisely inside the zone its star's luminosity defines as habitable. The zone does not care. It is a line drawn on a diagram. The planet's conditions are determined by physics far more complex than orbital mechanics. Earth holds liquid water because it sits in the zone, and it has the geology, the magnetism, the atmospheric chemistry, the tectonic activity, and the billion-year climate regulation to keep water liquid inside that zone. Every factor depends on every other. Pull one away, and the balance shifts toward Venus or toward Mars, toward fire or toward ice. The universe does not hand planets oceans for being in the right neighborhood. Being in the habitable zone isn't enough. 4.5 billion years ago, there were no oceans. There was no Earth, not in any form recognizable today. In its place was a disk of gas, dust, and rock, orbiting a newly ignited star. Everything in violent motion, nothing yet settled into stable orbits. Nothing yet cool enough to hold liquid on a surface. The early solar system was not a place of gradual, orderly construction. It was a collision zone. Rocky bodies, planetesimals ranging in size from gravel to small moons, swept through intersecting orbits, smashing together, breaking apart, reaccreting in larger masses, or being flung outward into cold oblivion by gravitational interactions with the growing giant planets. The Earth we stand on today accumulated from millions of these impacts over tens of millions of years, each collision adding mass, generating heat, driving the entire surface into a state of continuous molten chaos. During this period, Earth had no oceans. It barely had a surface. The question of where Earth's water came from is one of the most consequential unsolved problems in planetary science. It does not have a clean answer. Every hypothesis has evidence in its favor. Every hypothesis has evidence working against it. What all of them share is the implication that Earth's water was not inevitable, that the presence of these oceans required specific events, specific timing, and specific planetary dynamics that did not need to happen and may not have happened on most worlds that formed in similar conditions. Begin with the simplest theory. Water was already here. When the solar system formed from a collapsing cloud of gas and dust, that material was not pure. It was chemically complex, rich in carbon compounds, silicates, metals, and water ice beyond the frost line. As rocky bodies accreted in the inner solar system, they incorporated whatever material was locally available. Some of that material, even in the hot inner disk, contained water locked into hydrated minerals, chemical compounds in which water molecules are structurally bonded into the crystal lattices of rock rather than existing as free liquid or ice. This water does not evaporate when temperatures rise. It survives in mineral form until conditions cause it to release. The early Earth may have accreted with the significant supply of this primordial water already embedded in its rocky interior. As the planet's interior heated, from the energy of accretion, from the decay of radioactive isotopes, from the heat released by the iron core differentiating from the silicate mantle, that water would have gradually released from minerals and migrated toward the surface. Volcanic outgassing would have carried it into a developing atmosphere. As the surface eventually cooled below the condensation point, that atmospheric water vapor would have rained out, accumulating on the surface. In this model, Earth's oceans fell as rain from its own volcanic atmosphere, sourced from water that had been locked inside the planet since its formation. The evidence is not conclusive. Zircon crystals found in ancient Australian rock, the oldest known terrestrial minerals, dated to approximately 4.4 billion years ago, show chemical signatures suggesting liquid water existed on the surface even at that extraordinarily early date, barely 150 million years after Earth formed. If primordial water released through outgassing alone could account for early liquid surface water, the timeline is plausible. But the volume of water in Earth's current oceans, approximately 1.4 billion cubic kilometers, may exceed what internal primordial sources alone could supply, which is where the asteroid theory begins. The asteroid belt lies beyond Mars, between the inner rocky planets and the outer gas giants. It is a region of ancient material, objects that never fully accreted into a planet, disrupted by Jupiter's gravitational influence into a scattered population of rocky and metallic bodies. The inner asteroid belt is dry. The outer asteroid belt, beyond approximately 2.5 astronomical units from the Sun, is not. Carbonaceous chondrite asteroid, the C-type and Ci-type varieties, contain significant amounts of water in hydrated mineral form, sometimes comprising several % of their total mass by weight. During the first several hundred million years of solar system history, the orbits of the giant planets, Jupiter and Saturn, were not yet in their current stable configurations. As they migrated inward and outward during a period of gravitational reshuffling, they scattered enormous numbers of outer asteroid belt objects onto trajectories that crossed the inner solar system. Many of those objects impacted the early Earth, and the water locked inside their rocks came with them. This model, sometimes called late accretion or late veneer theory, predicts that Earth received a significant fraction of its water from hydrated asteroid impacts during the late heavy bombardment, a period of intense cratering that peaked approximately 3.9 billion years ago. The evidence comes partly from chemistry. The ratio of deuterium to ordinary hydrogen, the D/H ratio, in Earth's ocean water matches the D/H ratio found in carbonaceous chondrite meteorites more closely than it matches the D/H ratio found in most comets. Asteroids, not comets, appear to be the better chemical match for Earth's water. But that's not the real problem. The real problem is that matching ratios doesn't prove delivery. The match might mean asteroid water contributed to Earth's oceans, or it might mean the primordial Earth material had a similar isotopic signature from the beginning. The science does not yet fully separate these possibilities. What the isotope evidence does strongly suggest is that comets, the other major candidate for water delivery, were probably not the primary source. Comet water, as measured in multiple missions, including ESA's Rosetta spacecraft at Comet 67P, consistently shows a D/H ratio approximately twice that of Earth's ocean water. The numbers don't match. Comets may have contributed a small fraction, but they almost certainly did not fill Earth's oceans. The comet delivery hypothesis, once popular, has weakened significantly over the past 2 decades of direct measurement. The universe offered Earth an abundant supply of cometary water from the outer solar system, and Earth's oceans mostly don't appear to carry its signature. Now, consider what this means for the delivery problem as a whole. Earth received its water from whichever combination of primordial incorporation, asteroid bombardment, and residual cometary contribution the science eventually confirms. Because of specific events that depended on the particular architecture of this solar system. The migration of Jupiter and Saturn into configurations that scattered water-rich asteroids inward. The timing of that migration relative to Earth's formation. The gravitational geometry that allowed some of those scattered objects to reach Earth-crossing orbits rather than being ejected entirely from the solar system. The survival of enough material to deliver sufficient water before impacts tapered off. Change any of these factors and Earth might have received far less water than it did. Change them in the other direction and it might have received far more, enough to produce a water world, a planet covered entirely by ocean with no exposed land, where certain geological cycles cannot function, and where long-term climate regulation may be fundamentally different. The volume of water Earth carries is not random in its consequences. It is, again, a specific amount sitting within a range that allows the carbon silicate cycle to function across exposed continental rock, that allows subduction to carry water into the mantle and return it through volcanism, that maintains a balance between ocean basin capacity and total water volume that keeps continents exposed. Too much water and the land disappears. Too little and the oceans shrink below viability. Earth has approximately the right amount. Whether that precision was determined by the physics of planetary formation or by the specific chaotic contingencies of this particular solar system's early history is a question the field has not yet resolved. And then came the moon. Approximately 4.5 billion years ago, very early in Earth's history, possibly before significant water had accumulated on the surface, a Mars-sized protoplanet called Theia struck the proto-Earth at an oblique angle with enough force to partially vaporize both objects. Material from the collision was blasted into orbit and coalesced into the moon. The impact also reset Earth's rotational axis, altered its orbital parameters, and may have stripped away a significant fraction of whatever early atmosphere and surface water the young planet had accumulated to that point. The moon-forming impact is one of the most consequential events in Earth's history. And it was not a planned feature of planetary formation. It was a collision, dependent on Theia existing at the right mass, in the right orbit, at the right time in the solar system's evolution. Change the timing of Theia's impact, and a moon may not form. Change its mass or angle, and the resulting moon is different. And a different moon means different tidal forces, different stabilization of Earth's axial tilt, different ocean circulation dynamics, a different pace of geological and potentially biological development. Everything connects, and nothing about any of it was guaranteed. This is what makes Earth's water story genuinely difficult to disentangle. It is not one improbability, it is a cascade, each contingent event shaping the conditions under which the next one occurred. Primordial water incorporation depended on what material was locally available during accretion. Late asteroid delivery depended on Jupiter's migration path. The survival of that water after delivery depended on the atmosphere and surface conditions that existed when impacts occurred. The retention of that water across 4 billion years depended on magnetic shielding, climate regulation, and geological cycling that were themselves outcomes of earlier contingent events. Pull on any thread and the entire system changes. Planetary scientists working on water delivery models often describe Earth's water budget as sitting within a relatively narrow range of outcomes. Not so narrow that only one possible history could produce it, but narrow enough that the vast majority of simulated solar system analogs do not produce a planet with Earth's specific water volume, water location, and water retention history. Most simulated planets either receive too little water, lose too much of what they receive, or accumulate so much that surface conditions diverge fundamentally from Earth's. The ones that match Earth's outcome are the minority. Often the significant minority. There is a version of this story that is comforting. It says that water is common, solar systems are common, rocky planets are common, and given enough time and enough worlds, ocean planets like Earth must emerge frequently as a natural consequence of planet formation. That Earth's history, while complex, represents the high probability outcome for a rocky planet of similar size, at a similar orbital distance around a similar star. The evidence so far does not support this version. What the evidence supports is a story of accumulated contingency. Water arrived here through a specific chain of events that required particular solar system dynamics, particular giant planet migration patterns, particular impact histories and timing, particular post-impact survival conditions, and then further required the atmospheric, geological, and magnetic conditions explored in earlier sections to hold that water liquid on the surface for the subsequent 4 billion years. The scientific investigation of Earth's water origin is not a story with a finished conclusion. It is a story still being written by isotope analysis of meteorites, by missions to asteroids and icy moons, by computer simulations of solar system formation run across thousands of parameter variations, by measurements of water in the atmospheres of distant exoplanets. What those investigations have established so far is this: Earth's oceans did not appear because oceans are what happens when you form a planet. They appeared because a specific sequence of events in a specific order over a specific timescale produced this world and not some other version of it. The delivery was cosmic. The timing was critical. The outcome was not written in advance. Earth's oceans may be the result of cosmic luck. The sun is not passive. Every second it releases approximately 1 million tons of charged particles, protons, electrons, helium nuclei, streaming outward in all directions at speeds between 400 and 800 kilometers per second. This is the solar wind. It does not gust. It does not pause. It flows continuously day and night across every planet in the solar system, pressing against every atmosphere, interacting with every surface exposed to space, exerting a constant outward pressure that has persisted for 4.5 billion years. On most planets, this matters enormously. On Earth, you cannot feel it. You have never felt it directly in your life, and you never will. Not because it isn't real, but because something intervenes before it reaches you. Something generated deep inside the planet itself, invisible and ancient, running silently beneath your feet since long before life existed on the surface. Earth has a magnetic field, and without it, these oceans would not be here. The mechanism is deceptively simple in outline. At Earth's center, the inner core is a solid sphere of iron and nickel, roughly the size of the moon, surrounded by an outer core of liquid iron and nickel, approximately 2,200 kilometers thick. The outer core convects. Hot material rises, cooler material sinks. And that motion, combined with Earth's rotation, generates electrical currents through a process analogous to an electromagnetic dynamo. Those currents produce a magnetic field that extends far beyond the planet's surface into space, forming a protective bubble called the magnetosphere that deflects the solar wind around Earth, rather than allowing it to interact directly with the upper atmosphere. The magnetosphere is not a wall. It compresses on the side facing the sun, stretching and distorting as solar wind pressure varies, occasionally allowing energetic particles to funnel toward the poles, where they produce auroras, the visible evidence of charged particles entering the atmosphere, at the points where the magnetic field guides them. But for the vast majority of the atmosphere, the vast majority of the time, the magnetosphere holds. The solar wind streams around Earth rather than through it. The atmosphere beneath remains intact. Mars had this protection once. It does not anymore. The comparison is not abstract. NASA's MAVEN spacecraft, placed in Mars orbit specifically to study atmospheric loss, has measured the rate at which solar wind strips the Martian atmosphere today. The number is not large, at roughly 100 grams per second under normal solar conditions, rising significantly during solar storms. But applied across billions of years, even that slow rate represents the gradual erosion of an entire atmosphere. MAVEN's measurements, combined with isotopic analysis of Martian atmospheric gases, confirm that Mars has lost the majority of its ancient atmosphere to solar wind sputtering since its magnetic field collapsed. The water that once flowed on its surface followed the atmosphere into space, molecule by molecule, across geological timescales no single mind can truly comprehend. Earth retains its atmosphere and its water, partly because its iron core remains partially liquid, and partially because its rotation sustains the dynamo. If Earth's core cooled completely and solidified, the dynamo would stop. The magnetosphere would collapse. The solar wind would begin the same slow work on Earth's atmosphere that it performed on Mars. The process would take hundreds of millions of years, not decades, but the endpoint is not ambiguous. A planet without magnetic shielding, orbiting an active star, loses its atmosphere. A planet without an atmosphere loses its surface water. The sequence is fixed by physics. Earth's magnetic field has persisted for at least 3.5 billion years. The geological record confirms it. That persistence is itself not guaranteed. The field has weakened and reversed polarity multiple times throughout Earth's history, with reversal events taking thousands of years during which the field may drop to a fraction of its normal strength. Whether past reversals significantly accelerated atmospheric loss remains an open question. What the record shows is that the field has never failed completely. It has always recovered, always regenerated, always resumed its protective function before atmospheric erosion could reach catastrophic levels. But magnetic shielding is only the first layer. Even with the magnetosphere intact, some atmospheric escape occurs. Light gases, particularly hydrogen, can reach escape velocity and leak away from the top of the atmosphere regardless of magnetic protection. This is happening on Earth right now, at a slow and manageable rate. It happened much faster in the past when the young sun was more energetic and Earth's upper atmosphere was hotter and more extended. The fact that Earth retains water today despite this process means something else is compensating. A continuous resupply from below. Plate tectonics is not usually described as a planetary defense system. It is. Earth's lithosphere, like the rigid outer shell, is divided into approximately a dozen major plates that move slowly across the surface, driven by convection currents in the underlying mantle. Where plates converge, one descends beneath the other in a process called subduction, carrying ocean floor material, including water chemically bonded into minerals, deep into the mantle. That water doesn't disappear. It lowers the melting point of the surrounding rock, triggering partial melting, and the resulting magma rises through the crust and releases water vapor through volcanic activity. The water returns to the surface. This is a planetary water recycling system. Water lost into the deep earth through subduction returns through volcanoes. Water lost to the upper atmosphere is partially replenished from below. The cycle is not perfect. Some water is permanently sequestered in deep mantle minerals, and some atmospheric hydrogen escapes into space. But it operates across geological timescales in a way that slows the net loss rate enormously compared to a tectonically inactive planet. Mars, tectonically dead for billions of years, has no such cycle. Venus may have a form of volcanism, but without plate tectonics in the Earth sense, it lacks a subduction mechanism that pulls surface material into the mantle and drives the chemical return of volatiles through organized volcanic chains. A planet without active tectonics cannot recycle its water. It can only lose it. And this changes everything about how we evaluate other worlds. The presence of plate tectonics on a planet is not cosmetically relevant. It is not merely a curiosity of Earth's geology. It is part of the mechanism by which Earth has maintained liquid water for 4 billion years. Remove it, and the carbon silicate cycle described in earlier sections slows or stops. Remove it, and volcanic water return diminishes. Remove it, and the slow leak of hydrogen from the upper atmosphere accelerates relative to the replenishment rate. Earth's water budget is not static. It is a dynamic equilibrium maintained by ongoing geological activity. We do not know how common plate tectonics is on rocky planets beyond Earth. We have confirmed it on exactly one world. The conditions required, the right viscosity of mantle material, the right balance of internal heat, the right water content of the lithosphere itself. Water lubricates plate boundaries, making subduction easier. May or may not be common outcomes of rocky planet formation. Some planetary scientists argue that plate tectonics is a natural developmental stage for Earth-mass rocky planets with sufficient internal heat. Others argue that it is a geologically contingent outcome that required specific initial conditions, unlikely to repeat across most worlds of similar size and composition. The field does not have consensus. Earth has one data point. Every other claim is extrapolation. Then there is the moon. The moon is not decorative. It is not simply the reason for tides, though tidal forces have played roles in everything from coastal evolution to the mixing of early ocean chemistry. The moon's most significant long-term contribution to Earth's habitability is axial stabilization. Earth's rotational axis is currently tilted at approximately 23.4 degrees relative to its orbital plane. This tilt produces seasons. The northern and southern hemispheres alternately lean toward and away from the sun over the course of each year. The tilt itself varies over geological timescales, cycling between approximately 22 and 24.5 degrees over periods of roughly 40,000 years, driven by gravitational interactions with other planets. This range is small. The variation is slow. The resulting changes in solar energy distribution across latitudes contribute to ice age cycles, but they do not push Earth toward global freezing or runaway warming. Without the moon, this stability collapses. Computer simulations of Earth's axial behavior without lunar stabilization show chaotic oscillation of the tilt angle, swinging between near zero and 85 degrees over timescales of tens of millions of years. At near zero tilt, seasonal variation nearly disappears and polar regions may cool into permanent ice accumulation. At high tilt, polar regions receive direct sunlight during summer and experience extreme seasonal heating and cooling cycles, while equatorial regions may face reduced insolation for extended periods. Neither extreme necessarily prevents liquid water entirely, but both produce climate instability far greater than Earth has experienced across its history. And that instability could, over geological timescales, drive feedback loops toward either global glaciation or runaway warming. Mars, with its 2 tiny moons providing negligible stabilization, has experienced exactly this kind of axial chaos. Its obliquity, the angle of its tilt, has varied between near zero and approximately 60 degrees over its history, potentially explaining why its ancient water history is punctuated rather than continuous. Periods of high obliquity may have temporarily warmed the poles, releasing water from ice reserves, creating transient liquid conditions, then refreezing as the tilt shifted again. Mars's water history may not have been a steady decline into dryness, but a chaotic series of brief thaws within an overall trend toward permanent cold. Earth's moon is large relative to Earth, unusually large for a rocky planet of Earth size. As established in the previous section, it formed from a catastrophic impact that was itself a contingent event. The impact happened, the moon formed, and the moon's gravitational influence has maintained Earth's axial stability within a narrow range for billions of years, smoothing the climate variation that would otherwise have produced far greater instability than Earth's geological record shows. Remove the moon, or replace it with smaller moons providing less stabilization, and Earth's climate history likely looks substantially different. Whether it would still be an ocean world today under those conditions is genuinely uncertain. Consider the full system. Earth keeps its oceans because it generates a magnetic field that deflects the solar wind and prevents catastrophic atmospheric stripping. It keeps its oceans because plate tectonics maintains a water recycling system that counteracts the slow leak of hydrogen from the upper atmosphere. It keeps its oceans because the moon stabilizes its axial tilt within a range that prevents the extreme climate swings that could drive permanent global glaciation or runaway warming. It keeps its oceans because its atmospheric composition, regulated by the carbon silicate cycle and the biological influence of life itself over the past several billion years, maintains surface temperatures within the liquid water window, despite a sun that has brightened by 30% since the planet formed. Each of these systems is independent in its origin. The magnetic field depends on the iron core. Plate tectonics depends on mantle viscosity and internal heat. The moon depends on the specific geometry and timing of the Theia impact. The atmospheric carbon cycle depends on volcanism, weathering chemistry, and for the past several billion years, biology. None of these factors required the others to develop. None of them was guaranteed. All of them had to emerge and sustain themselves simultaneously across deep time. On Mars, the magnetic field failed. One protector gone, and the cascade began. On Venus, the runaway greenhouse overwhelmed whatever protection the planet may have had. On every airless world in the solar system, Mercury, the moon, countless smaller bodies, there is no protection at all, and no atmosphere, and no water at the surface. Earth's situation is not the default planetary outcome. It is the outcome of a planet that developed, by accident and contingency, exactly the suite of protective systems required to hold liquid water against the relentless pressure of the universe to take it away. The sun has been trying to strip this atmosphere for 4.5 billion years. It has not succeeded because Earth is not defenseless. Earth keeps its oceans because it can defend them. The Kepler Space Telescope stared at a single patch of sky for 4 years. Not sweeping, not scanning. Staring. Fixed on one region of the Milky Way containing approximately 150,000 stars, measuring the brightness of each one with enough precision to detect the faint dimming caused by a planet passing across its face. The data it returned transformed planetary science. More than 2,600 confirmed planets. Thousands of additional candidates, a statistical picture of planetary abundance so comprehensive that astronomers could, for the first time, extrapolate with reasonable confidence across the entire galaxy. The conclusion was staggering in one direction and sobering in another. Planets are everywhere. Nearly every star appears to host at least one. The Milky Way alone likely contains more than 1 trillion planets. More planets than there are stars because many stars host multiple worlds. The universe, it turns out, is not a vast emptiness punctuated by rare solar systems. It is a vast architecture of planetary systems stacked across every region of the galaxy, around stars of every type and age. For a moment, this seemed to make the search for ocean worlds simpler. If planets are abundant, Earth-like planets must be abundant too. Then the filtering began. Of those trillions of planets, the overwhelming majority are gas giants or ice giants. Jupiter-class worlds, Neptune-class worlds, hot Jupiters orbiting so close to their stars that surface temperatures exceed the melting point of iron. No surface, no possibility of liquid water in any form accessible to chemistry. Eliminate them. What remains is a smaller subset of smaller rocky worlds. Super-Earths and Earth-mass planets, the kind that can hold a solid surface. The kind where liquid water is at least physically conceivable. Filter again for orbital distance. Of those rocky worlds, only the fraction orbiting within the habitable zone of their host star qualifies for further consideration. Many orbit too close, where tidal locking and stellar radiation make surface conditions inhospitable. Many orbit too far, where temperatures fall permanently below the freezing point. The habitable zone narrows the candidate list significantly, not to rare, but to a much smaller fraction of an already filtered set. Filter again for stellar type. Most stars in the galaxy are red dwarfs, smaller, cooler, longer lived than the Sun, and far more magnetically active in their youth. Habitable zone planets around red dwarfs orbit so close that tidal locking is almost certain, and the stellar flare environment during the star's first billion years may strip planetary atmospheres faster than they can be replenished. The fraction of red dwarf habitable zone planets that retain stable atmospheres across the timescales required for complex chemistry is unknown. But current models suggest it may be substantially lower than the fraction around Sun-like stars. Filter for magnetic shielding. Filter for tectonic activity. Filter for water delivery history. Filter for axial stability. Filter for long-term atmospheric regulation. Each filter removes planets from the candidate pool. Each filter is independent. Each represents a condition that had to be met on Earth and that most planets will fail. This is the core of what planetary scientists call the rare Earth hypothesis. The argument, developed formally in the early 2000s and contested, refined, and debated ever since, that the combination of factors required to produce a stable, long-lived ocean world is so specific that such worlds may be genuinely rare across the galaxy, even given the staggering number of planets the universe contains. The hypothesis is not universally accepted. It cannot be because the data required to test it rigorously does not yet exist. We cannot directly image the surfaces of Earth-sized exoplanets. We cannot measure their magnetic fields from light years away. We cannot determine whether they have plate tectonics or large stabilizing moons or the right water volume delivered at the right time by the right class of impactors. We can measure atmospheric composition, partially approximately for a small number of planets, using transit spectroscopy. And even that measurement is at the edge of current instrumental capability. What we can say is this: of every planet observed so far, not one beyond Earth has been confirmed to have liquid water on its surface. Not one confirmed ocean. Not one confirmed tide. The catalog of known worlds grows larger every year, and the confirmed ocean planet count remains exactly where it has been since the first telescope was pointed at the sky. 1. But that's not the real problem. The real problem is not the absence of confirmed ocean worlds. It is the mathematics of what would be required to produce them. Take the factors enumerated across this documentary and treat each as a probabilistic filter. Assign rough estimates, even generous ones, to the fraction of planets that meet each criterion. The numbers compound in a direction that should produce genuine discomfort in anyone who assumes Earth is ordinary. Suppose 1 in 5 rocky habitable zone planets forms with sufficient water delivery. Suppose 1 in 3 retains a magnetic field strong enough to prevent catastrophic atmospheric stripping over billion-year timescales. Suppose 1 in 4 develops plate tectonics and the associated water recycling that prevents net ocean loss. Suppose 1 in 5 avoids runaway greenhouse warming or permanent global glaciation through sufficient atmospheric regulation. Suppose 1 in 10 has axial stability sufficient to prevent the kind of climate chaos that Mars has experienced. These numbers are not precise. They are informed guesses, placeholders for processes we do not yet fully understand. But multiply them together, even with generous assumptions at each step, and the fraction of rocky habitable zone planets that meet all criteria simultaneously becomes very small. Not 0, not even necessarily less than 1 in a million, but small enough that the galaxy, despite its trillion planets, might contain ocean worlds in numbers that are vast by human standards and vanishingly rare by cosmic ones. And this changes everything about how we understand our position. There is a tendency, natural, understandable, and probably wrong, to assume that because Earth exists, Earth-like planets must be common. The reasoning is seductive. We are here, therefore conditions permitting us must not be extraordinarily rare, because extraordinarily rare things do not produce observers capable of noting their own rarity. This argument, a version of the anthropic principle, is philosophically valid as far as it goes, but it does not tell us how rare Earth actually is. It tells us only that Earth's conditions were not impossible. The distance between not impossible and common is where all the important scientific questions live. The James Webb Space Telescope, operating since 2022, has begun returning atmospheric data from exoplanets at a level of precision previously impossible. Its early results have been illuminating in both directions. It has confirmed the presence of carbon dioxide in the atmosphere of a sub-Neptune exoplanet, the first direct detection of a carbon-based molecule in a planet's atmosphere. It has also returned data on several rocky planet candidates that appear preliminarily to lack substantial atmospheres entirely. Bare rock worlds, stripped or never equipped with the atmospheric envelope required for surface liquid water. The data is early. The sample size is small. The instruments are still being calibrated to this unprecedented task. But the early returns do not suggest that Earth-like atmospheric conditions are the default outcome for rocky planets. They suggest that thick, stable, chemically complex atmospheres, the kind that enable liquid surface water, may require specific formation conditions that many rocky planets simply do not meet. step back further still, out of the galaxy entirely. Consider what the universe at the largest scale implies. The observable universe contains an estimated 2 trillion galaxies. Within those galaxies, an estimated 10 to the power of 24 stars. A number so large it has no meaningful everyday analog. If 1 in a billion of those stars has a planet that meets all the conditions for a stable ocean world, the total number of ocean planets in the observable universe would still be 1 quadrillion, a number that seems to make Earth unremarkable. But consider what fraction of those worlds formed early enough for complex life to develop, orbiting stable stars in the right regions of their galaxies, surviving the sterilizing radiation of nearby supernova and gamma-ray bursts, maintaining their conditions across the billions of years required for biology to reach the point of self-reflection. Each additional filter reduces the number further. The universe is old enough and large enough that even extremely rare events happen somewhere. But the question of whether ocean worlds like Earth are common enough to make intelligent life abundant in the galaxy, or rare enough that Earth represents something genuinely unusual in its cosmic neighborhood, remains one of the deepest unanswered questions in science. What the evidence gathered so far permits without overreaching is a statement of considered probability. Earth is not clearly typical. Every measurement of other worlds, every analysis of planetary formation dynamics, every study of atmospheric stability and magnetic protection and water delivery points in the same direction. The conditions that produced this ocean, this atmosphere, this magnetic field, this stable axial tilt, this 4 billion year continuity of liquid water on a rocky surface, these conditions required things to go right in a specific sequence that the universe does not appear to routinely provide. Look at Earth from the distance at which Voyager 1 photographed it in 1990. A pale blue dot suspended in a beam of sunlight, occupying less than a pixel of the camera's sensor, surrounded by the blackness of a solar system that from that distance looks empty in every direction. Carl Sagan described the image as a demonstration of our smallness, our fragility, our responsibility to one another. All of that is true, but the image communicates something else too, something that has only become clearer as planetary science has advanced in the decades since. That blue is the ocean. That ocean is what makes Earth visible at all from deep space. And that ocean, the science increasingly suggests, is not what planets look like. It is what this planet looks like. One planet around one star in one arm of one galaxy, distinguished from nearly every other world we have observed by the presence of that blue, that water, that impossible continuity of liquid on a rocky surface across geological time. The universe contains trillions of planets, and we have confirmed oceans on one of them. The number may grow, it almost certainly will, as instruments improve, and our ability to characterize distant atmospheres sharpens. Future telescopes, the Habitable Worlds Observatory, proposed for the 2040s, may detect the spectroscopic signatures of liquid water or biological activity in the atmospheres of nearby Earth-sized planets. That detection would be one of the most significant moments in the history of human knowledge. But as of everything we currently know, everything we have measured, every planet we have studied up close, and every exoplanet we have characterized from afar, the ocean remains here. The water remains here. The conditions that produce and sustain it remain here, on this one world, maintained by a set of planetary systems whose simultaneous presence may constitute something the universe rarely assembles. We did not earn this. We did not engineer it. We inherited an improbability so layered and so ancient that most of its critical chapters were written before the first living cell divided in the early ocean. The least the evidence asks of us is that we stop treating it as ordinary. Earth's oceans may be one of the universe's rarest miracles,